All right, let's talk about some piecewise functions. So, as the name might suggest, piecewise functions are pieces of a different functions that are all graphed in the same place. Let's consider the following piecewise function. We've got f of x equal to x squared plus 1 when x is less than 2, and 7 minus x when x is greater than or equal to 2. And so what we're just gonna graph both pieces. So the graph of this function is gonna look like y equals x squared plus 1 to the left of x equals 2. And it's gonna look like y equals 7 minus x to the right of x equals 2. So let's just graph both functions completely. Y equals x squared plus 1, that looks like your normal parabola shifted. Which way? Up. So that's I heard one person say left. I just want to point out, if it was left, it would be x minus 1 quantity, or sorry, it'd be x plus 1 quantity squared to be left. But here the plus 1 is happening after we're doing the squaring, so it's shifting it up. So it's going to have the point 0, 1 and the point 1, 2. I don't have to plot all these points, but I'm going to. We have the point 2, comma 5, etc. So it would look something like this. Welcome, Taz. Thank you. And I do want to focus on one point in particular. Well, actually, 2 points. I really want to focus on the point 2, comma 5 here, because that point is going to be kind of the end of one of the pieces, right? This first piece, y equals x, thank you, y equals x squared plus 1, we're only going to have when x is left of 2. So that 0.25 is going to be the end of it on one side or the other. We're only going to have everything that's to the left of this. So everything over there. We're not going to have any of this part up here. Another thing I want to point out, just because I saw people make this mistake on the quiz and some other places, it's not a huge deal, but I've seen people getting the x and y coordinates of the intercept interchanged. So just be careful. When it's the y-intercept, right, the x coordinate is 0, which comes first, and the y coordinate is 1, which comes second. If it's the x coordinate, right, or I should say, thank you. If it's the x-intercept, right, if you're somewhere on the x-axis, well, I'll just wait until I draw the x-intercept on the next one. So the next one, we've got the line y equals 7 minus x. And since I know it's a line, I'm just going to do the usual thing I do for a line, which is I'm going to find the y-intercept. So I'm going to set x equal to 0. I'm then getting y equal to 7 minus 0. And then for the x-intercept, same deal. I'm going to set y equal to 0. I get 0 equal to 7 minus x, which ends up being x equal to 7. So there are my intercepts. I'll try and draw this so it doesn't look terrible. And that's always the goal, so it doesn't look terrible. And then I will just point out this point here is the point 7, comma 0, where x is 7 and y is 0. And this point here is 0, comma 7, where x is 0 and y is 7. Just be careful with the labels. And then I'm also going to point out that this graph as well at 2 has a value of 5. So I plug in 2, I get out 5. So I want this graph, it's in red, I want everything here that's to the right of 2. And this graph over here in green, I want everything that's going to be to the left of 2. And it doesn't actually make a huge difference in this particular example, but we should be careful and say, well, I really want the 7 minus x graph when x is bigger than or equal to 2. So I'm actually going to want to include that point there. Now, since they meet up at the same point, right, both these graphs hit the point 2, comma 5, we're not gonna have to worry about it, but we'll see in the next example how sometimes that doesn't happen. So now we're gonna put it all together in one big graph. So left of 2, there's 2. Left of 2, I have the parabola. So I have everything from 2, 5. So actually I want to point out, when I start graphing this parabola here, I don't actually get the point 2, comma 5. Right, that point, since I'm only including the parabola up to, sorry, you guys can see that right now. I only want the parabola when x is less than, but not equal to 2. And if I was just graphing that part on its own before I graph the other part, here's what it would look like. and have an open circle at 2, 5, and then I have the rest of the graph to the left. So I have the point 1, 2, 0, 1, negative 1, 2, negative 2, 5, and everything to the left. So there's the first piece of that graph. It's the graph of y equal to x squared plus 1. Oops. When x is less than 2. And we do have a hole there, right? So as x gets closer and closer to 2, the y values get closer and closer to 5. X could be 1.9, and y would be 4.61, and x would be 1.9999999, and y would be very, very close to 5. But we actually never get the value 2, 5 on this portion of the piecewise graph. So there's a hole there. But then the other piece comes along and fills in that hole. And so the other graph happens to have the exact missing point. So we could say, oh, well, the other one, we get that there. And then we get every part that's to the right here, which looks like that, and has the x-intercept of 7. So this part here is the y equal to 7 minus x, when x is bigger than or equal to 2. Question? Yeah.
So it's okay if like we fill in the circle, the open circle.
Right. Yeah. So yeah, if they match up like that, you totally should. But we're going to see in the next example that the line is going to get moved down a little bit, so they're not going to be up there. So we're just going to have an open circle. Yeah.
Thank you.
Yeah.
Where did the 5 come from?
The 5. That's
like 2, 5.
No, that's a good question. So the 5 came from the pieces of the piecewise function. So when I look at a piecewise function, I'm usually focusing a lot on where you change from one piece to the next. So this graph, this function f of x, changed from the parabola x squared plus 1 to the line 7 minus x when x is equal to 2. And so what I did was I said, I'm going to substitute in 2 for x and see what the y values are. So when I plug in 2 here, I get 2 squared plus 1, which is 5. And when I plug in 2 here, I get 7 minus 2, which is also 5. So they match up. But that's actually a really good question, because that's a piece of advice I would always say to do. Whenever you have a piecewise function, you always want to plug in that value and see what the y value is getting closer and closer to, or is. You have a question, Willie?
Yeah. So for the parabola, you only want the values that are less than 2.
So I want all the, yeah, yes, I want all the values when x is less than 2, right? So I want everything to the left of 2. And for the line, I want everything when x is bigger than or equal to 2. So I want everything that's to the right of 2. So often when I do this, if I'm graphing both pieces at once, I look at this and I say, okay, and I kind of do this thing where I kind of scribble it in. Like I want all of this part here, which I know doesn't look nice, but that's okay. It's not my final result. And for the red one, I want everything that's to the right of 2. There's no up or down. Right? We're not going up, down. We are only thinking left, right, when we're thinking about a piecewise function. So when I look at this graph, I look at x equals 2, and I want everything to the right. And then I put them together in one graph. Good question. Other questions? Any questions from the Zoom land? Oh, I didn't make the Zoom private. So yeah. Now your questions are seen by no one but me, I think. Let me double check. Yes, you're free to ask questions. Yeah.
So for example, for the y equals x squared plus 1, could you draw a line at x equals 2, or would that look like an asymptote?
Well, here's what I say. If it's not your final result, I would say sure. But on your final graph, I really would prefer not to have a vertical line there, because it's not that it necessarily looks like an asymptote. It just looks like extra that we don't really need. So what I would try and say is try and think about their, like, I mean, on this one, I have like the grid, right? I can see the line x equals 2 right there, that, right? If I go up this way here like that, I just don't want that to interfere with my final kind of picture. But you totally could here, right? Like here it'd be totally fine. Like, I'm going to draw a line here, like that's the cutoff. I'm going to draw a line here, say that's the cutoff. That would be totally fine. But I do think it's probably not great to put on your final. Other questions? Okay, we'll do another example that's very similar, but a little bit different. I have more examples in mind to do after the 3 that are on this handout. So don't worry if you're like, James, you'll have 3, but I got lots of them. So we got extra. I got extra. So this graph is just very slightly different. Instead of having y equals x squared plus 1, now it's just the regular nice parent graph y equals x squared. So we can, although you don't have to, but we certainly can draw the pieces separately. So if we want to, we can be like, okay, over here, I'm going to draw y equals x squared. I know it hits the origin. And then what other point on y equals x squared am I concerned about for this particular piecewise step? What x value is really, really important to me? 2. So I'm going to plug in 2 and get y equal to 4. So I have the point 2, 4. And we know that we want everything to the left of 2. So I want everything to the left. So I was looking at the piecewise graph here and said, oh, at 2, we're going to change from this piece to that piece. So what I did was I said, well, I need to know what's going on with this piece. So I plugged in x equal to 2, even though you're right. It doesn't say x equals 2 there. It says x is less than 2. But since I know that x is getting super duper close to 2, like x could be almost 2, I'm just going to plug in 2 to see the y value that it's going to be getting close to, which is going to be 2 squared, which is 4. So I'm plugging in the 2 that we're not quite getting there into the function x squared there and getting 2 squared. And then we're going to do the same sort of thing for the other piece. Now, the other piece we've already graphed. We graph it again. 7 minus x. We know how to y-intercept of 7 and an x-intercept of 7. And again, we're concerned with what's happening at x equal to 2. So I'm going to look at 2 again and see that here I've got the point 2, 5. And we can see that these are not going to meet up. That's okay. We want everything to the right of 2, 5, including that point. And so what I might have tried to emphasize here is I actually am not going to want the point 2, 4. So I really want to draw an open circle there. To be like, okay, we don't want 2. We don't want 2, 4 because x doesn't actually get to equal 2 for that piece of the function. We do want the point 2, 5 because when x is 2, that's in the second piece of the piecewise function. And when you plug in 2, 7 by 6, 5. So here's how this graph is going to look. So again, I'm thinking about 2 being the break point here. So I usually go from left to right, although it doesn't matter actually. It's just kind of what I do. So I'm going to draw the left function. So I'm going to draw y equals x squared, but only up to the point 2, 4, and I'm going to exclude the point 2, 4. So what I really should actually do is just start by drawing an open circle at 2, 4. And then I know I have these other points, 1, 1, 0, 0, negative 1, 1, negative 2, 4, etc. It looks kind of like this. And it stops right there. That's the left piece of my graph. That's x less than 2. And now for the right piece, I want x to be greater than or equal to 2. And I'm going to get this part of the line, starting at the point 2, 5, and going down to the right. And it is pretty standard to label both this point 2, 5, and this point that we don't have, which is 2, 4. Now, you wouldn't really need to label them here because there's this grid and we've done a very good job of graphing things precisely. But if I was doing this more freehand, which I'll show you another example of, I would be more kind of label happy. There was another thing I want to say here. This graph is a function, It passes the vertical line test. There isn't any x value that has more than one y value associated to it. You might be like, James, x equals 2 looks kind of sketchy. I'd be like, it does, but when x is 2, you only get one y value. You get y equal to 5. The other thing I'll mention, even though this is not something we're going to talk about in this class, is that this function is definitely not continuous. Right? If you draw it, there's a very clear break where you have to lift your pen off the paper to get to the next point. Not that that's a very formal definition of continuity, but it is a nice kind of way to think about continuity. Yeah.
Do you like us to label like X and Y intercepts?
Yeah, it's good to be in the habit of labeling those intercepts. So either label them or make them extremely clear. Right. So if you're and this was definitely something like on the quiz, I was like, or maybe on the homework. Like if it was very clear that you made like this many marks, you went over that many, like if I could tell what the point was by the way your graph was, great. But if you labeled it, that's also great. So here, obviously, we can all see the x-intercept is 7, the y-intercept is the origin. I don't think we need to label those here. But if our graph was less beautiful looking, which I'll show you some examples of very shortly here, then I would label things. I have to be able to see this movie. Oh yeah, question. This is one function, but we're taking two different pieces of other functions and putting them and making a new function out of it. So yes, this is a single piecewise function. We're calling it f of x, but you're right. We're using multiple other functions to make this new thing.
If you included the 2, 5, would it not be a function? I mean, 2, 4.
Correct. Excellent observation. Yes. If we included this point, it would no longer be a function because there would be an x value 2 that had 2 different y values associated to it. And the way you can make it not a function very easily is just by slapping on a less than or equals to there. Because then if it was less than or equal to 2, you'd have 2 different places where you had to plug in the 2. Usually people aren't trying to do that. Like no one's trying, in most of the time, no one's trying to make a piecewise function that isn't a function. They're not trying to be like, oh, it's defined here and secretly defined there as well. No, that's not what we're going for. So no one's trying to do that to you. No one's going to ask you if this thing's a function and secretly make it not a function. But yeah, but you're right. It's very much so. If we did define it at 2 in 2 different places, it would not be a function. Good questions. You guys asked some excellent questions. Okay. Let's look at the next example. It has a few more pieces. So I'm going to graph this thing without, I'm always like kind of torn between, but I want to just graph it. Now I'm going to graph all the pieces. So you don't have to graph all the pieces separately, is what I'm really trying to say. You can tell me I'm going to graph x squared to the left, and then x minus 1 between 0 and 1, and then the natural log of x after 1. Well, let's put them all together. Let's show them all still. So we already have y equals x squared up here. If you can't see it up there, can we see if we do that? Not really. Let's just draw it again. It's an easy one to draw. It's just your usual parabola. And we want everything on which side? The left of what?
0.
Right. Or the y-axis, if you want to call it that. So x equals 0, or the y-axis, we want everything to the left. So we want everything here. And then f of x equals, or y equals x minus 1. Put that over here. That's just a straight line. You could think of it as a straight line y equals x shifted down 1. Or you could also think of it as shifted right 1 if you want to just find the intercepts. But it is the line y equals x minus 1 with a y-intercept of -1 and x-intercept of +1. And we want everything between 0 and 1, but not including either endpoint. So actually, we want everything from here to here, but we don't want to include those intercepts. Itchy nose. Okay. And then finally, when x is bigger than or equal to 1, we have the logarithmic function. Natural log of x, log base 2 of x, whatever the base is, we know the general shape. Right? The usual logarithmic function that hasn't been shifted or stretched or anything has a vertical asymptote at 0, has an x-intercept at 1, and then just continues on like this. We want everything on that graph where x is bigger than or equal to 1. So we want everything from here to the right. So now we're going to put all the pieces together. And so I know that this is the part that's going to kind of have the endpoints not included, right? Because this is the one where x is between 0 and 1, sorry, but not getting either endpoint. This y equals x squared, we're going to have just this left half here. So 0, 0, negative 1, 1, negative 2, 4. There's my parabola where x is less than or equal to 0. There's my x squared where x is less than or equal to 0. None of this labeling needs to happen on your graph, right? I'm showing you all the things because I always try to show you all the things, but right, you do definitely not need to write this when you're graphing these things. And then for x between 0 and 1, I want this little portion of the line. I'm not going to get the y-intercept there, right? I don't get the point 0, negative 1. I get an open circle at the point 0, negative 1. And then I also don't get the point 1, 0. Well, that's not true, right? I mean, I wouldn't get it from this portion, but then I know I'm going to end up filling it in from this portion here, because this portion does have the point 1, 0. So instead of making a big deal about it and be like, oh, I don't get it, draw it up a circle, I'm just going to pretend like, well, we almost get there. And then I really want to see that. We almost get there. And then this next piece, oh yeah, we want all of you, including the x-intercept 1, 0. And then drawing this is never my forte here. It's kind of like that. Oh, sorry, thank you. Yeah. Let me zoom back up just a little bit. I was just writing the natural log of x when x is bigger than or equal to 1, and then in this little small part here, right there between 0 and 1, it's y equal to x minus 1. So that's the process in general for drawing a piecewise function. You just want each piece, however much of it you've got. And typically we kind of have all the usual kind of parent functions. We've been kind of shifted. Really, we kind of, mostly when we're doing piecewise functions, it's kind of like pieces of parent functions or maybe shifted parent functions, but nothing really more complicated than that. And I thought I saw a hand over there. Yeah.
Why do we want the point 1, 0?
Well, because even though we didn't get it here, right? If I was actually graphing the portion of that, I would have everything from 0, negative 1 to 1, 0, but not including either endpoint, right? That's exactly what you're saying, right? We don't get those points there. But then from this next piece to the right of it, we do get the point 1, 0, because the natural log graph does have an x-intercept at 1, 0. It's kind of like how in the first example, right, when we were drawing the piecewise function here, at first we didn't have the point 2, 5 because we were missing it from the parabola, but then we filled it in from the line because the line did have the point. We got so much time. We might end early. We might not. We'll see. Let's do more examples. So let's, that piece of paper does not look excellent. Let's use the other side of it. Blank pages, I know. How exciting. So this is where I get to make stuff up. Let's look at this one. Let's graph x equal to, let's make it a 3-parter. Let's make it, yeah, sure. X plus 3 when x is less than or equal to 1. Sorry, negative 1, apologies. x squared minus 1 when x is bigger than -1, less than or equal to 2. And then finally,
That's a negative one.
it does. I squeezed that negative in there at the end. 5 when x is bigger than 2. So again, just so everyone has it, it's x plus 3 when x is less than or equal to -1. It's x squared minus 1 when x is bigger than -1 and less than or equal to 2. And it's equal to 5 when x is larger than 2. So let me show you how I would do this without drawing all the pieces. We'll still draw all the pieces after, but I want to kind of show you, like, you don't have to draw all the pieces ever, really, if you don't want to. So I'm going to start with the leftmost piece. And typically, usually when people write these out, it's usually from left to right, it's from top to bottom. So they, most of the time when they're writing these, the top part is the part that's the leftmost part, and then the next most, right? And then the next most, and so on. Sometimes they write them out of order, but usually they don't. I will almost always, I will write them in order unless for some reason there's never a good reason not to. So a couple of things I'm thinking about as I go here. When I'm looking at x plus 3, I'm thinking about what the intercepts might be. So if I was actually going to graph y equals x plus 3, sorry, you can't see everything, apologies. If I was thinking about y equals x plus 3, even though I'm not going to graph it, I would say, well, I know there's a y-intercept at 0, 3, because when you plug in 0 for x, you get 3 for y. I'm not going to get that point because I have to stop at -1. I don't get all the way to 0. But it still helps me think about the shape of the graph. And then there would be an x-intercept. Well, if I plug in 0 for y, x would be -3. So that is a point I'm going to get because x being -3 is definitely less than x being -1. Now, for this first piece, what's the other place I really should think about? Not 0, 3, not -3, 0, excuse me, but I should think about when x is equal to -1 because that's going to be kind of a break point. We might change, well, we definitely will change from one piece to another piece there. So if I plugged in -1 for x, I would get y equal to -1 plus 3. So here's what I'm going to do when I draw this first piece, which I know is a line. I'm going to draw the point -3, 0 and -1, 2. And I'm going to try not to be super precise about it. And I know I include that point because it is included. So here is my x-intercept, -3, 0. Here's my endpoint, -1, 2. That's a 2, believe it or not. Okay. And I'm trying to think. And you can see if we kept going with this graph to the right, it would hit its y-intercept of 0, 3. We're not going to continue it, but it would continue in the right way. Okay, so now the next piece here is x squared minus 1. So we have y equal to x squared minus 1 when x is between -1 and +2. And what I would probably do is see what's happening at each of those endpoints. So even though I can't actually get a value of -1, I'm still going to check it out. So if I plugged in -1, I would get y equal to -1 squared minus 1, which is 1 minus 1, which is 0. And then if I plugged in x equal to 2, I would get y equal to 2 squared minus 1, which is 3. So here are the values I'm starting to get. I know this is a parabola. Sorry, I started saying one thing and then I changed directions. This is a parabola shifted down 1. So usually we'd have the origin as the vertex, but we know it's going to be 1 lower. And we've almost got this point, except not really, right? -1, 0 should be open since x is greater than, but not equal to -1. Looks like that. And then we're going to end up over here at this point 2, 3. So here is the piece. And if you wanted, we could also plug in x equal to 1 and see that there's a point there. There's the piece of the parabola we get. Everything from -1 to +2, not including the very left point at -1. I should probably label this as 2, 3. I don't think I need to label this one here because it's on the axis and I've made it clear it's 1 to the left. So I think everyone would be okay to be like, oh yeah, it's almost the point -1, 0. Questions about anything I've done so far?
You only want to find the y-x-intercept for a line.
Say it one more time, sorry.
For the line,
Yeah.
you want to find the x and y-intercept, not for the parabola.
Well, that's a good question. Yes, so I definitely could have thought about doing that as well. I kind of knew what was going to happen, to be honest. I was like, I know I'm shifting it down 1. I know that I'm going to get the x-intercepts to be -1 and 1 and the y-intercepts to be -1. So it was kind of like, I didn't want to spend the time writing that just to say it, but you're right. We do want to think about those intercepts. So I should definitely be, there is an intercept there at 0, -1. There is an x-intercept there at 1, 0.
How much information and like examples like that do you want us to write on?
There's never a good answer to that question. So for example, here, I think I've written the appropriate amount so far. I haven't finished the problem yet, because there's still this last part here, but I do think it's important to make it clear that these are x-intercepts. I think what I've done is, right, like, I think we could all agree, I hope, that everyone can see, oh yeah, there's an x-intercept at +1 there, there's a y-intercept at -1, and there's not quite, but we're getting very, very close to the point -1, 0 there. There actually isn't an x-intercept there.
Like all the calculations on the bottom, those are not like.
I feel like none of this needs to be written.
Okay.
I'm showing you this stuff so that you can see it, but I think you are all capable of saying, okay, I want to get these points. Well, for this graph here, I know there's an x-intercept at -3, because if I set this equal to 0, x has to be -3. And I know if I plug in -1 for x, I get y equal to 2. So there's my point -3, 0, there's my point -1, 2. I think you should label them, but I don't think you need to show this work down here that I've done. Similarly, for this parabola, we know it's been shifted down by 1. So I know I have this vertex at 0, -1. And then I'm looking at what's happening at either end. So when x is -1, or if x is almost -1, y is going to be 0. If x is 2, 2 squared minus 1, y is going to be 3. So yeah, I don't think you need to show all these calculations. I'm showing it so you can see what's happening, but not because you need to do that. All right, last part. The function's 5 when x is bigger than 2. So when I plug in 2, what do I get? If I could plug in 2. Sorry, you guys can't see that. If I could plug in 2 to this function, this piece of the function, what would I get? I know it's a terrible question because there's nowhere to plug x in. So if I plugged in x equal to 3 or 4 or 7 or a billion, the thing I'm always getting out is 5. There's nowhere to put the x. So what's happening is we have a constant function. And it looks like just a horizontal line. And we almost get the point 2, 5, but not quite, because x can't actually ever equal 2 on this piece of the function. Question? That's exactly the same as saying y equals 5. Because what we're really saying here, right, you could look at each of these as y equals x plus 3, y equals x squared minus 1, y equals 5. That would also be a perfectly fine way to imagine it. And then you're like, oh yeah, y equals 5 when x is bigger than 2. Y equals x squared minus 1 when x is between -1 and +2. And y equals x plus 3 over here. So yeah, if thinking of it as y is helpful, definitely think of it that way, because it is. We're just using f of x because it's what people do.
I know technically like this is all one function. But,
Yes,
like for like a single function, can it just like a single parabola?
Sure.
Does it still have a hole in it, or does it have to have something like?
not you. Well, so there is a way to make a parabola have a hole in it if you want. It's not, I mean, yeah, sure, why not? We got time. So here, let me just point out, this is something that does come up. Functions can have holes if you make them undefined. So here's a real quick example to address your question, which I think is not, I definitely think is worthwhile. So let's say you had something like this. I'm going to make it not terrible. Let's say it was y equal to, how not terrible can I make it? Sure. X cubed minus 2x squared divided by x minus 2. And hopefully all of you would tell me this function is undefined where. What can x definitely not equal? 2, for sure. If x is 2, what do I get? Well, I get 0 in the denominator. 0 in the denominator is always an issue. Now, what I should really actually point out here is that if x is 2, we actually get 0 divided by 0. Right? 2 on top gives you 8 minus 8, which is 0. 2 on the bottom gives you 2 minus 2, which is 0. So if x were equal to 2, you would get what's called a 0 over 0 indeterminate form, which is definitely something you're going to see next quarter when you take Calc 1. A lot of 0 over 0 stuff. And so what's happening in this particular example is, well, I'm going to factor. What factors out from the top? Thank you. Yes. What's left? X minus 2. Can I cancel those things? Yes, but. So now here's the important question. Are these the same? Is this function x cubed minus 2x squared over x minus 2 and this function x squared the same? Well, almost all the time, yes, except at one point. 2. For this function, y equals x cubed minus 2 squared over x minus 2, this function is undefined at x equal to 2. But anywhere other than 2, it's the same as x squared. So these functions are actually the same everywhere except for 2. For example, and this is where things are going to get a little bit gross, let's pick a number close to 2. Let's pick a number like 1.9, because I have to find the square of it. So if x is 1.9, well, x squared is going to be 1.9 squared, which I will tell you is 3.61. What if we plug in 1.9 here? It looks terrible, but we've already done the work because we know that this is equal to this. And if x is 1.9, what's 1.9 minus 2? Negative something. And 1.9 minus 2 divided by 1.9 minus 2, those just divide out to 1. So the whole point here, and this is really kind of important, especially in your future mathematical careers, not that it's important for like class today, but like these cancel out as long as x isn't 2. And so as long as x isn't 2, you're going to get the same value. So whether you're plugging in 1.9 to x squared or plugging in 1.9 to this other gross thing, x cubed minus 2x squared over x minus 2, it's still going to equal the same thing. So here's the real point. This function and this function are the same everywhere except at 2. And the only difference is this function has the point 2 comma 4. This function has nothing. So here's y equals x squared. Oh, okay, maybe. Oh, sorry, we'll get it because it looks terrible. Here's y equals x squared, kind of. And here is the other function. Y equals x cubed minus 2x squared over x minus 2. And its only difference is that at the point 2 comma 4, it's going to have a hole. But in every other regard is exactly the same as the other function. So there's a very long answer to your question. I hope it helps. So yeah, functions can't have holes at places where they're undefined. Sometimes they have vertical asymptotes at places where they're undefined. So that's a discussion for another class for sure. Here we're only really getting open holes when it's kind of like the end of where a function is being defined. Other questions before we do one more example? Nika. Okay. Let's do something fun. So let's say we want to graph this piecewise function. X equal to the square root of x minus 4. Oh, that's a bad start, James. Why is it a bad start? Well, because I want it to be all the way to the left, but square root of x minus 4 doesn't go all the way to the left. That's okay. We'll deal with it. We'll say it's for x between 4. So this one's gonna be a little out of order. That's all right. X between 4 and fine. Be difficult. So now we got to pick something to the left of 4, something to the right of 8. Okay, we can do it. How about we do? Sure. Let's just make it. Why not? Here's our piecewise function, written very much out of order. So I'm going to read it in order. It's equal to the function 3 when x is less than 4. It's equal to the square root of x minus 4 when x is between 4 and 8, including 4, not including 8. And it's equal to 9 minus x when x is bigger than or equal to 8. And I do think it's worth our while to graph each of the pieces separately. I feel like that's like definitely if you find this difficult, challenging, or not, right? If you just find it helpful, do that, right? I don't like to do it because I've been doing it for many, many years and it's time consuming, but I'm not you, right? So definitely, if you want to take the steps to do the things, take the steps. So I'm going to graph all the pieces. You know, it was a lot of work. It's okay. So square root of x minus 4 looks like your usual square root function shifted 4 to the right. So 4, boom, square root. Boom. But we only want everything from 4 to 8, so we're going to stop at 8. And I don't want to include that point there, so I know it's going to have an open circle. I really just want all of this. Okay. And then when x is less than 4, I want the function to equal 3. Well, I should just graph all of 3. There's y equal to 3. Now I want everything where x is less than 4. So everything to the left of 4. And finally, I have this 9 minus x function, which is a downward sloping line. These ones are like the ones where it's something minus x are always nice because it's, the x and the y-intercept are the same. They're both whatever that number is. This one has a y-intercept of 9 and an x-intercept of 9. And then I want everything where x is bigger than or equal to 8. So I'm going to start at 8. I'm going to include that point, and then I want everything to the right of it. That point, by the way, is 8, 1. I suppose I should label the points, at least somewhere. That point's 8, 1. that point there, that's kind of the break is 4,3. Obviously, the y value has to be 3 there. There's no other choice. And then here, if I plug in 8 to the square root function, what's my y value going to be? That's a good question. Right, square root of 4, which is 2. Yeah. So again, we know we're not actually going to get to that point, but it's still an important feature of our graph. Okay. Now we put it all together. And usually when I'm putting it all together, I start from the left. So I know I want to definitely have some room on the right here. So I'm going to make sure I have like a 4 and an 8 and a 9. I know important things are happening at 4 and 8 and 9. So let's see. To the left of 4, I just want 3. Zero, 3. And then we know we want this square rooty piece between 4 and 8. So it's going to start there at 4, 0. And then it's going to go over to 8. And we're not going to get up as high as 3 because we're ending at 0.8, 2. So we're going to like right about there. But open circle. Sorry. Kind of looks like it's filled in there. It's not meant to be filled in. It's meant to be open. Terrible. You can kind of pretend that it gets open there. Okay. Say that one more time. Yes, 4, 0. This one here. Yeah, that one's filled in. That one definitely is not. And then the last part, bigger than or equal to 8, we want the graph here that's starting at the point 8, 1. So start at 8, 1, and then it's going to have the x-intercept of 9, 0. So the one thing I'll say, another thing I'll say about labeling these things is you don't want them, you don't like, obviously I want you to label them because they're important, but also don't want to clutter, right? Like I feel like my graph is a little bit cluttered with all this labeling. So if you want to like be like, I don't want to draw that right there, like, okay, 8, 2 is like right there or something like that is also fine. As long as it's understandable, it's really okay. Or if you just write down, we have the point 8, 2, and then we have an open circle at, sorry, we have the point 8, 1. We have an open circle. If you write those words instead, that's also fine. Just so try to make it clear. I mean, I don't know how to be super clear about that other than if someone else is reading it, they should be like, oh yeah, I know what you meant there. I can see that there's a point there, and there's a point there, and there's almost a point there.